Environmentally friendly coatings technologies such as powder, ultraviolet cure, high solids, and waterborne systems are gaining importance every year due to the increased cognizance of coatings emissions and their environmental impact. Conventional waterborne coatings still possess significant levels of volatile organic compounds, or VOCs, stemming from their co-solvent content. The Thames-Rawlins research group is engaged in the development of alternative technologies from natural, renewable resources to manufacture environmentally responsible coatings with zero VOCs, little to no odor, and reduced reliance upon petroleum-based monomers. Naturally occurring vegetable oils such as soybean oil and linseed oil have to be chemically modified to facilitate their reaction with other monomers. The vegetable oil derivatives, vegetable oil macromonomers, or VOMMs, are low molecular weight compounds that retain the unsaturation characteristic of vegetable oil precursors. VOMMs have been synthesized with a variety of functional groups, making them a versatile monomer for diverse applications including emulsion polymerization and textile finishes. Emulsion polymerization involves polymerization, which is the process of building up large molecules by combining monomers. Emulsions are formed by monomers, surfactants, and water. VOMMs are blended with other monomers and surfactants and fed into the reaction kettle. An initiator solution is fed into the reaction kettle through a separate tube. The entire process takes 4 hours. The capillary hydrodynamic fractionator is a valuable tool to monitor the particle size within the latexes. The reaction calorimeter is used to measure the heat of polymerization. The heat given off during polymerization is characteristic of the monomers employed and is a useful parameter to monitor the progress of the reaction. A React-IR uses infrared spectroscopy to continuously monitor the concentration of functional groups and provides real-time data regarding the progress of the reaction. The first step in making waterborne architectural coatings is the formation of a pigment grind. Here, mechanical agitation is used to disperse pigments into water using dispersing agents. In the next step, the latex and additives are blended with the pigment grind to complete the coating formulation. A Higman gauge is then used to determine the fineness of the pigment dispersion. Coating viscosity is determined using an ICI cone plate viscometer for high shear rheology. The finished coating is applied onto Linetta charts and scrub charts for evaluation. A gloss meter is used to measure the reflectance of a coating. Scrub resistance to determine the ability of the coating to withstand cleaning. Block resistance to ensure that the coating does not stick to itself on windowsills and door frames. Colorimeter helps us to measure the relative color of a coating based on the 3 primaries. The colorimeter can also measure the ability of a coating to be penetrated by light, also known as the opacity. After drawdown, cuts are made into the film to form 60 quarter-inch squares in the center of the film. Panels are soaked for up to 30 minutes in ambient tap water and then mounted in a washability tester with 20 milliliters of water. The panel is then scrubbed for up to 500 cycles or until all the squares within each block are completely removed. Test quantifies the loss of adhesion to a substrate after exposure to high humidity, condensation, or precipitation. Commercial particle boards are synthesized using urea formaldehyde resins, and these slowly liberate formaldehyde over their lifetime. The Thames-Rawlins research group has synthesized formaldehyde-free particle boards using soybean protein-based adhesive. Soybean protein is dispersed in water, thoroughly blended with appropriate additives to form the adhesive. The adhesive is then blended with wood furnish in a high-speed Henschel mixer. The wood furnish adhesive mixture is formed into a block and loaded into a composite press where it is heated under high pressure to 193 degrees Celsius for 7 minutes. The finished board is cut to specific sizes and tested for mechanical and physical properties. Key properties of interest are modulus of rupture, modulus of elasticity, internal bond, water absorption, and thickness swell. VOMMs have yielded promising results as durable press finishes for textiles. The fabric is immersed in the finish for 2 minutes and then wrung to remove the excess finish. The fabric is then cured at 150 degrees Celsius for 6 minutes. This cross-links the VOMM with the cellulose. The treated fabric is tested for crease resistance by determining the wrinkle recovery angle, smoothness, whiteness, and mechanical properties such as tensile and tear strength. VOMM-based latexes have been formulated into paper coatings following a process similar to producing architectural coatings. The paper coating is applied to the test strips using a wire-wound rod and cured at 105 degrees Celsius for 1 minute. The coated paper is tested for porosity and roughness using a Parker print circ, and for dry pick strength following a tappy test method using an IGT inking machine.